Hello everyone, my name is Yin Pan and I am studying the Speech and Hearing Research Group at the University of Sheffield. My supervisor is Heidi Christensen. Today I'm going to present the work we have done, Acoustic Feature Extraction with Interpretable Deep Neural Network for Neurodegenerative Related Disorder Classification. This work is supported by Marie Curie Grant, the European Union's Horizon 2020 research. In this presentation, we will introduce the work we have done from these parts, the research background and the research difficulties, the feature extractor we designed considering the research questions we face with and the difficulties we hope to solve. Then we will introduce the database we used in the experiment. Finally, we will give the details of the experiment setup and discuss the results we achieved. In this presentation, first of all, let's start with the research background. Our research is related to the speech-based cognitive disorder detection, like the neurodegenerative disorders or mild cognitive impairments, ND and MCI for short. ND and MCI are caused by slow progressive loss of neurons in the central neural system, leading to an irreversible selection loss of brain functions. Before diagnosed as ND, people often diagnosed as MCI. According to the statistics, about 10% to 15% people living with MCI will convert into having Alzheimer's disease. And the problem is ND cannot be cured, so the early and accurate detection is of great importance. For ND and MCI, the main symptom is the memory impairment. Also, the speech and language can be affected decades before the diagnosis. And compared with the other diagnostic tools, speech-based technology is non-invasive, potentially more sensitive than pen and paper tests. As for the research difficulties, for constructing the speech-based dementia detection system, it highly depends on the performance of the acoustic features. According to the previous research, arriving at a consensus for best feature size has proven to be very challenging. And considering the development of neural network in speech-related fields, constructing a task-specific deep neural network can be very useful. So the first difficulty is, how could we design a feature extractor with deep neural network? And compared with the handcraft features, more information exists in the raw view form, but extracting the critical information directly from the raw view with limited data is of great difficulties. So we need to consider how to extract a task-specific feature from the raw view with limited data. And also, the medical-related research fields care more about the interpretability of the system. How to meet the requirements of the interpretability should be considered. Considering all the requirements of a desirable system, we build a system as shown in the slide. In this system, SIGINT is as the first layer. As we know that SIGINT can convert faster compared with CNN. At the same time, it defines the convolutional layer with the seek function and initialize with mailbank parameters, making it more interpretable. Followed by the SIGINT and CNN layers, we use bidirectional LSTM for learning the time sequence information, and followed by an attention layer, which is used for weighting the importance of the learned features. In this system, after training with the development data, the parameters are set fixed. The experiment data is input into the system, and the output vector of the attention layer, or dense layer, is used as the representation of the input view segments. Let's have a look at the recordings we used in the experiment. For the IVA data, it is collected by the Department of Neurology, the University of Sheffield, based at the Royal Hampshire Hospital in a real clinical setting during 2016, 2017, and 2018. While doing the test, People are asked to answer the questions designed to mimic the neurologist and patient conversation happening as a part of routine diagnostic assignments. The conversations are recorded in this process. To do our experiment, only the speech recordings from the participants are used. And our classification tasks are all binary classification, including the classification between HC and MCI, HC and ND, and we also combine the recordings from MCI and ND as one class for testing our system. More information can be found in the table 1. And to provide a reliable result, tenfold cross-validation is used on the relatively small dataset, and each fault is fixed for all the experiments we present. For the recordings from the IVA dataset, the average length of the recording is about 9 minutes, which we can find it in table 1. But this length is too long to work as the input of our designed feature extractor. Considering the situation, we utilize a 2-second window for tracking the wave and use those chunks as the system's input. To compare the two feature size, the compare and LS10 feature vector extracted by OpenSmell works as the baseline features. And to test the performance of the features output by the designed feature extractor and the baseline features, we utilize the most common classifier, SVM and logistic regression. The classification results for trunk level and recording level are shown in the table 2 and table 3. By comparing the results with each table, we could find that comparing with the S10 and compare feature size, the classification results of the learned dance feature and the attention feature are superior for the 3 classification tasks we performed. And also, the performance of the dance layer. The performance of the dance and attention features do not differ much for either of the 2 classifiers. And by comparing the results between the 2 tables, we could find that the performance of the features and the classifiers at the recording level is better, but consistent with the performance under the same situation after majority voting on the trunk level labels. Considering the interpretability of the requirements of the medical research, we plot out the cumulative filter responses learned from the 3 tasks. The line with different color represents the different classification tasks. Both lines are the average response of the tenfold cross-validation, and thin lines are the response for every fault-trained network. The black line is the initialized mailbank parameters. We could see that more detailed information is learned by Signite filters compared with the initialized mailbank filters. By observing the cumulative filter responses of the 3 tasks, we find that the filters concentrate on the low frequencies. This means low frequencies can be the critical information for classification. Also, more filters are set in the low frequency zones when the symptom gets worse. For example, the difference between green line and red line. By comparing, we can find that the peak of the red line in low frequency zones is higher than the green line's peak value. And to explore the corresponding response of the filters for the 3 tasks, we plot out the output of the Signite. The output of the Signite layer is the A-tip dimension. Only the first 5 dimension is plotted out. And each row corresponded to the average vector of the recording across all the corresponding 2-second waves. For all the recordings, we could find that high values and main differences are concentrated on the first several dimensions. By comparing the average response of each recording within the figure, we could find that the response of the low frequency also gets higher when the symptom gets worse. So these things are quite interesting, and we will do more exploration in the future research. And these are the works we have done, and thank you so much for listening. If you are curious about it or have any questions, please contact me.